So, good morning, participants. Good morning. Um, I welcome you all at MNIT Jaipur, and we have gathered here to understand. We started with machines which were compute efficient. Then we thought that can machines think? And then we said, yes, they can think, then now make them to learn like humans. And now where we are, we want the machines to be creative so that they can create creative content like us. So they can create images, they can create storylines, they can create videos, and a lot of things which comes under art, music, whatever comes under the creative field. So that is what is generative AI. And we are now here to study this with the help of an expert who has immense experience in this area. So let us welcome Professor Kiran Raja. He is faculty at Department of Computer Science, Norwegian University of Technology and Science. So I request our HOD, Dr. Mushtaq Ahmed, to welcome Professor Raja by presenting a bouquet. This is just a formal to make him welcome in this department. एक पिक्चर मुश्ताक आप आओ नहीं ये आप ही आओ या हाँ दोनों बीच में आओ हाँ So we have a 5-day program. We have shared the schedule with you. Every day we'll be having 2 tea breaks. For lunch we'll be giving you coupon. Just next to our building there is a canteen and you can choose what you want to eat there. Okay. And apart from that, in the evening, Jaipur is a beautiful place. I suggest that you go and see around and enjoy your stay. We'll make sure that you enjoy your stay and sir will make sure that you gain maximum from this. Thank you very much.
Before that,
okay, just a moment. If sir wish to say something, I'm so sorry.
Thank you, ma'am. As you know that in this very new session, so we are in that stream of providing multiple circular sessions. Okay. So among that, this is the one of the most important part currently, which is being used by the industry and academia at large, where the challenges pertaining to the need and requirement in such an efficiency that the adaptability of the person would be more. So for that purpose, this generative AI has emerged as a key point for providing those type of that features, additional features, which would enhance the output and that is more acceptable. So, similar type of that work that we have undergone in a multiple different type of the platform, and I hope this again with that the expertise like Kiran Raja, Professor Kiran Raja, he would you can enhance additional with the uh, live support or some uh, programming part which you will be able to understand that and a hands-on experience that will give you the idea where the deep areas are and where you can meet those type of the requirement. So pertaining to this, the challenges are there that the type of the data, we have the text, image, audio, video, and multiple type of those challenges pertaining to that conversion and use of that is there, where this generative AI is playing a very much role. So I hope that this particular GAN program would give you in offline mode the maximum benefit, and those who are connected in the online, they would also use that in their system and platforms to get more learn about the generative AI and its use. So I congratulate Madam and thanks Professor Kiran Raja to come over here and sparing his valuable time to provide the participant a valuable information. And I hope that this program will be very successful. Thank you. Thank you.
You know, it's yeah. Okay. Okay. Very good morning, and I'm very happy that Professor Neetanen invited me here, and Maipal took care of me very well yesterday. It's always a pleasure to be back in Jaipur all the time. So I was in Jaipur in one of the conferences when Professor Neetanen organized some years ago. I think 2016. Cities in 2017, I think.
And I think you won best paper.
Yes, also the best paper award. Yeah, it was very kind of you. So we did. So I'm very happy to be back here again. So that being said, I'll take this opportunity first of all to thank MNIT and all the organizers, Maipal and Professor Neeta, to invite me here, and then I would first introduce you some of the two groups that I work with. I work with two specific groups which work on particular topics, and then I'll start with the lectures. And I'm very, very sorry to disappoint you with all the image, text, and nice content that you can generate with generative AI today. Today, I'm going to stick on to very basics of fundamentals of machine learning. So once we have that in place, then from tomorrow onwards, we can build up on that one. Is that okay? And the lecture is also not one way. So anytime you have any question, you will stop me, right? So then we have a discussion and then we proceed from there. So it's not a monologue. I would prefer it to be a more of a dialogue. Okay, good. So this kind of, I was looking for some nice cartoons yesterday, and then this cartoon kind of summarizes whatever we are doing in machine learning today, right? It's usually it's not the system itself, uh, but it's more about the data. So what we are talking, whatever we are doing in machine learning, whatever you are putting in, if you're putting in garbage, you're getting garbage out, right? So it's 90% of the time your data that tells anything. So back in the days when, at least when I was educated, so we were all looking at the interesting features, and then we would engineer the features to have a meaningful machine learning system. So now we are in a luxury situation where we have abundance of data. which means the data can actually lead you to meaningful insights. So we just dump the data and then we keep on learning the system until the system tells what we want the machine to tell, right? Okay, so that being said, pre-log to the system. So I work with two different groups, as I said before. So one of them is called as the Norwegian Visual Computing Lab, or more popularly known as Color Lab. Uh, it's a very small group as compared to many of the big universities in India. So we are a research unit within the Department of Computer Science, and we are located in three different campuses. And our group was somehow like this. And at the peak of the summer, let's say when the temperatures hit plus degrees, let's say 20 degrees or two-digit numbers, then our group combines together with the other groups, and we are a bit bigger group. And this is a snapshot of our picture of our lab. So what do? We are a group of 5 professors and 7 associate professors and 6 permanent researchers, and the postdocs and PhDs. You can just take it for now, but the numbers keep on updating all the time. And when it comes to the diversity of the group, we are very diverse. We represent approximately 29 nationalities according to the last numbers, and they're all from different countries. As you can see, India is one of the countries that is having highest representation within the lab. So we have the Norwegian members. Apart from Norwegian members, it's the next numbers are from India and then from rest of Europe. Just to give a brief introduction about the teaching study programs, we do teach a lot of bachelor programs. Especially, we are focused around bachelor in programming. This is a typical BSc program in India, and then we have a bachelor in engineering, which is on computer science. And then we have two different master programs. One of them is applied computer science, and the second one is called computational color and spectral imaging, where we go deeper into the spectral imaging aspects. And then we run, of course, the PhD in computer science. Okay, I'll not bore you with so many of these things, but the only thing that I want to tell you here is that when the lab was started back in 2001, approximately around that time, so the whole idea was that how can we consistently reproduce color? Now, this sounds very trivial, right? So the color that you see on your newspaper is very different from the color that you see on your iPhone or on your Android phone, right? So we want to keep the color very consistent. So now the whole research is around focused around that, which would mean that we look at human visual aspects, we look at the computer vision aspects, and we look at combining both of these things together. I'll not bore you to the history of the lab, just some major milestones here. You can see that in 2001, the lab was started, and 2003, there was this major grant on research on the research project grant on multispectral imaging. It was more of a strategic grant. And then from then on, we have a number of projects. And 2007 was the first PhD we had. And 2019 is a number of different projects. What is currently running right now is, let's go back here. So we have 2 EU ITN projects, which is typically a doctoral training project, which means that we are training a number of doctoral candidates, PhD candidates. And these are under 2 projects called as Change and Appears. And then we have 2 research projects which are very specifically devoted to understanding the visual aspects of human vision. And then the same aspects on medical imaging. The SpectraSkin is one of the projects where we are working on detecting early stage of cancer using the regular images. And from then on, we have a number of projects which are CAPS Network, Capsule, and NetApp, and so on. 2 active projects are Capsule and CAPS Network, where we are looking at medical imaging of, or let's say medical diagnostics of human intestine, the GI tract. In the GI tract, what we want to do is that we want to send the pill instead of having this endoscopy. I am not sure. I think most of the audience here looks very young, so I'm not sure if you have undergone any endoscopy. But for those of the older generation, they would have undergone an endoscopy. It's a very painful procedure, and nobody wants to do that. So what we are doing right now is that we are, instead of sending the endoscope into the human body, we are just sending a pill, which is typically like your, let's say, paracetamol or ibuprofen. It's as small as that, and then it goes through your entire digestive system, and then it exists, and then there's a video that is captured for almost 10 to 12 hours. And this video is very huge, right? And no doctor wants to sit and watch this video. 12 hours of boring intestine tract. Nobody wants to watch that. But then if you don't watch it, then we are going to miss out on the key pathological information. So what these two projects are doing are having a huge collaboration with number of countries: China, US, Germany, Norway, and India. All the 5 partners are looking at different aspects of the problem, and then we are trying to solve different problems within the domain. One such example is early pathology detection, and the second one is summarizing the whole video, and then the third one is explaining the aspects of medical imaging to doctors, right? So end-to-end systems are being developed in those projects. Okay, so then I'll stop at this point, and then we have a whole week ahead of us, so where we can sit and chat, and then we can discuss different research topics. If you want to know more about this, I'll be very happy to chat during the breaks. And then let's see, I also work in a different group, which is more close to what Professor Nina and Professor Nitanen and others are working on. The group is called as Norwegian Biometrics Laboratory, and then we have 5 permanent faculty members and number of PhD students that are working with us. And this was a picture that was taken in 2012. The key idea here is to show that we are not a group that is working very independently. We have a number of collaborations again. As you can see, we have a number of publications, a number of these publications are coming out of as a result of collaborations. I'll not get into the details of this, but we do cover a number of aspects such as physiological and behavioral biometrics. And one of our key aspects recently has been biometric template protection, and then with presentation attack detection and morphing attack detection. I'll take these terms for examples in the course during the next few days. But for this point of time, I just wanted to know that we do cover both aspects of physiological and behavioral aspects. And then when it comes to the funding, we have a number of national projects, including some of the projects from national agencies such as the Research Council of Norway. And then we have agencies such as the German Research Council. And then we do have agencies like Athena, which is like a center of excellence for AI research. And then we work on EU-funded projects such as IMARS, Einstein, and Popeye. Number of these projects will be referred during the course of next couple of days. And then from time to time, we also work with industry. For those of you who have taken your Aadhaar card, I'm sure you recognize the name Morpho there, IDEMIA Morpho. They are the providers of the census for ID card enrollment, such as your iris enrollment, your fingerprints and face, and so on. We do work from time to time with them. And then in addition to that, we do work with companies like Dermalog, Crossmatch, Fujitsu, and so on. Okay, so probably I should not get too much detail into this, but I'll come back to this. And then just to give a very brief introduction to what we are doing with generative AI, this is one typical example what we are doing with Gen AI. So here, the idea is that we have a face which is in the central part of the image here, and then very often what happens is that when people are going to take an image to give the passport or to get an ID card, they end up giving some unintended poses, which might include a smile, which might include some expressions, which might include some anger, and so on. What we wanted to do is, in this work, where I was not particularly involved, our group members worked on generative AI to simulate different aspects of expressions. So if you have a person who's smiling and then you transform the person from smile to the normal face, this is what is accepted in the ID cards, and then we could use it in the systems further on, right? So this is one of the examples, which I'll come back to it later on, I think approximately in day 3. And then we do have just not the technology development, but we do have 2 companies which are working very closely with us, where we take the idea from the research from, let's say, from the lab, and then take it to the market, right? So we do have the prototype development all the way to the market deployment with these 2 companies. One company is called Mobile, and the second company is called IBA. Mobile works mostly on the physical biometrics, and the IBA works on your behavioral biometrics, the way you type, the way you walk, and so on. Okay, and then I'll come back to other aspects later on. With that being said, I think I would start the course with something very, very trivial. So what I want you all to do is to, generally most of the people say that you should not open your smartphones, but I tend to go to the other way. I say that, okay, let's all open our smartphones and then start putting in something here. Again, this is a very informal, uninformal setting. So I would want to know what is that audience wants, right? So there is no meaning in the, there is no point in me giving the lectures without meeting your expectations. So let's just try to understand what is that you are expecting from the course, and then we can go ahead from there, and then I can adapt some of the lecture content. All right, so if you can open your smartphones and then just type in that code, or you can scan the QR code. And again, this is a very anonymous survey, so don't worry about anyone having the identity revealed. Right, so whenever you are ready. No, you can just log into the, you can just type in the code there, 88583094, and then you should be able to get in. No, just go to the menti.com, and then on that you can type in the 8858, it should work. If you have troubles, I can. Menti.com, yeah.
What we are supposed to do?
Just scan the QR code and then
Scan the code.
Scan the code, and then you should be able to go to the link. No, not working? Okay, let me try. Yeah, I think I'm getting it. I don't know. So we should be landing in this particular slide. If you just scan the QR code, you landed, no? Right. You also, yeah. Okay. So just wait for a moment. I'm waiting for everybody to come on, and then we can proceed. Okay, we don't have to rush, right? So we have a whole 5 weeks, 5 days ahead of us. So we make some compromises. Sometimes the breaks will be shorter, lunch breaks will be shorter, but the whole idea is that we have meaningful discussions here. Okay? Okay, everybody is here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I think we have good numbers here. Okay, let's try to understand where are we standing now. So here I have just put 3 options. I have some experience in using AI ML, as in just using them, right?
QR code again.
Oh, sure.
You can
Just
use that particular.
the code as well.
It's there on the header itself.
The top 8858.
.com. You can go there and type it.
Okay, this is a very nice distribution. So we have 7 people that have used AIML to some extent, and 6 people who are not used, and 7 who have used it somewhat. So the idea here is that those people who have used, I'm very happy that you'll be my discussion partners, and those people who are not used, I'm also very happy that we'll be able to learn something together. Okay, so don't be very skeptical about not having used it. So I'm just getting a feel of the class right now. Good. So whenever you are ready, we can go to the next slide. Ready? Okay. Okay. So how many of you have actually built something in AI system? Excellent. So we have now the number of people that are not built AI systems increasing. I'll just tell you why this is very interesting in a couple of moments. Okay, how many of you actually built some machine learning models? Now, I understand there's a very thin, fine line between the AI and ML systems, but at least those of you who have built something in the ML models. There are 4 people who have, 5 people that have actually built something, 14 people that have not built. Okay. All right. So this is also very interesting. Now let's take the other side of the picture. Let's say, how many have actually built something based on statistics? Okay. So this is also very interesting. So some people who actually said that they built something in AI, use AI, some in machine learning, but then here we see the numbers actually kind of increasing. They say that they've used statistic-based models, which means that I think you're already half the way to learning AI, right? So most of our models are typically based on statistics and probability. I'll connect in the first lecture how these concepts are connected to generative AI. But any keywords that come to your mind at this point of time when you talk about AI, ML, or statistics? Transformers, very advanced. OpenAI regression, excellent. LLMs, generative AI, gradient descent, linear algebra, random forest, excellent. GANs, variational autoencoders, saving time, diffusion models, SVM. I'm very happy to see some of the classical names here, SVM and random forest. Data classification, prompt engineering, GMMs. Somebody is a fan of classical machine learning here. Linear algebra, clip models, morphing, hacking, and regression. Morphing, we'll talk about that one. Hacking, not so much. Regression, yes. GNNs. This is also very wonderful domain. I think Mahipal is your expert here for GNNs, HMMs, clustering neural networks, ChatGPT. I think a number of people are actually focusing more on LLMs, diffusion, GANs, and generated discriminator architectures. It's fairly fully justified. You are in that generation where uh, everything is more on the diffusion models, and I also see that using models, API models, to show off, very apt. A lot of these startups are actually doing that, so they are integrating API models and then just calling the machine learning models on the back of the stage. Uh, software information theory, wonderful. So this is what we're going to talk about it today. Mathematics in AI. Moderations. I'm curious about this one. What is the moderation? Somebody would like to comment on that? Moderations. Oh yeah. Right. So, and we are talking about the ethical use of the data and ethical use. Oh yeah. Okay. So the change in data, the transformations in data that can lead to unintended consequences. Okay, excellent. Help in research. They do massively help in research. I can say that we have used some of these well-known topics within the research, and they do have quite an impact on research. Defect detection, yes, certainly we'll talk about them. LCM and explainability. The most common recurring topic here is that, as you can see, it's the generative part, right? It's all LLMs, it's all on GANs, it's all on diffusion, and so on. So we will talk about these things in the next few days. But I'm also very happy to see that there are people who are talking about very classical machine learning. So I'm personally a fan of classical machine learning. So the more you understand the classical machine learning, it's easy to translate it to the new generation architectures. So we will talk about a number of these topics during the course here. I think. Okay. So let's say, what do we want from this course? Again, it's totally fine if you just want to have fun, to understand the topics and so on. But I also understood there is an exam in the end of the course, so some of you might be willing to do that, targeting the exam. So it doesn't matter if you are here to have fun or if you want to learn something new. We can cater all the kind of audience here.
What do you mean by is the test?
I think I heard that there is an exam at the end of the year.
There will be an exam on the last day.
So I just wanted to ask.
What do you mean by I want to ace the test?
So there is an exam in the last day, on the last day.
Uh-huh.
So some of you might be targeting to get the best grade in the exam.
Score in the
Oh. Strongly disagree.
I would totally agree with you. I must say that I'm a bit disappointed by just to have fun, because a lot of the topics that we learn, it's never about learning, it's about having fun, right? Along the lines, you will learn something new, you will use the course to create something new, but the important thing is that we need to have fun, right? So the idea here is that let's make the course more fun, more discussions, more interesting conversations, rather than just me talking here. So I hope that we will turn this number around by end of this today's session, or at least by end of this week, so that we understand that we had fun instead of just having one-way lectures. Good. So, what do you already know about this subject? So, where should I begin from? Should I begin all the way from something very, very trivial, or should I directly jump into the transformers? So, where do you think that we should start with linear algebra, or all the way to the to coding the models? Linear algebra. Begin with some basics. So I understand there are some experts sitting in the hall. So I would, I'm not surprised that there is a wide variety of audience here. All right, so we start somewhere from the basics. I see that a number of people are also pretty new. Basic ideas, some feature engineering.
I think so you already have your slides, so you start from there, that covers the basics also.
Yeah, so I just,
This is because it is the Gyan is already expecting that one lecture.
oh, okay.
It's online, getting transmitted.
Okay, so then, I'll come back to
You
this.
do this later on.
Yes, okay, all right. So I can come back to this later, but I think I get an idea on how we are planning to do, how the audience is spread. Okay, good. So then we have some basic idea of what is that we are looking at today. So we will look at three different aspects. We will look at statistics and AI, how they are connected, and then we will look at probability and AI, how they are connected, and then finally I'll end up with machine learning and AI. So most of you might be already thinking about the interconnections between all these three aspects. Let me just give a very brief history of what has happened in the couple of years. One of the important thing is that most of us think AI is very new, right? So it's actually not very true. If you go through the history of AI, you can see that the Turing test was conducted somewhere in 1950s, where they were trying to see the reasoning of machines. And then a number of things happened during the 1950 to 1966. 1966, is where they're talking about this perceptrons and backpropagation and so on. And then came the period between 1966 and 1997, approximately around that time, which we call as AI winter. It's called as AI winter mainly because there were not enough systems that were able to do the ideas implemented, right? So the whole of the research went into a controversy, and then suddenly people said it was impossible to implement these systems. And then came the Deep Blue, which was around 1997, where they started talking about, well, now we are back in the game, that we have the computation resources to do that, and so on. And then from 1997 onwards, there are a number of new milestones that has happened. One of the milestones that we could also talk about is the Watson, which came in 2011, which was from Watson. Approximately around the same time, there was also this Siri. Most people who would use iPhone, you would have used this feature. And then a number of other models also came, which popularized the deep learning for common man. So what we are talking about, we are not talking about a set of experts sitting here, set of people who know how the machines work, but rather the people that are out on the streets, right? The people that are common man who use this technology on a day-to-day basis. And I think its biggest attention that came was around 2017 when AlphaGo was released, and this kind of bet the best chess player in the world. Now that people were in the position to tell that the machines could start thinking about logic. I don't know how many of you play chess, but it's a very complicated game, right? So you need to plan your moves ahead, and then you need to go back and then track your every single step. And every time something changes, you need to make a new strategy. That means that there is a continuous thinking process, and this was possible in 2017 when the machines were able to do such a strategy and develop the and win against a human player. Okay, so then if we are looking at the broader area of applications, I'm talking taking the name of neural networks in a very broad aspect. I'll come back to that later on, but just to give a wide variety of applications that we can think of image and speech recognition, which has been there for many years. And then NLP, most of you use the ChatGPT either to translate something from Hindi to English, English to Hindi, and so on. And there is the extensive use of the neural networks in NLP. I also heard last time when I was in India, Mahindra was launching the self-driving cars, even including Tata, and it's also quite common with many other producers such as the German car producers or the US car producers who are actually developing these autonomous systems, and self-driving cars is a prime example of that.
I don't know what is the meaning of neural.
Okay, all right. So again, maybe I should have been a bit more careful there. So the applications of neural networks itself, I'll come back to it later. But what we are talking about is the broader area of applications of AI, what we call as artificial intelligence.
So in the afternoon, after 3:30, we'll have a hands-on exercise where you'll understand neural networks.
No, what is the
So-
meaning of neural word?
Neural
English
is
word.
that brain, biological brain,
Okay.
which is artificially designed for the machine, then it is artificial neural network.
Okay, thank you.
So it's a series of connections between the visual system and the brain system, right? So you have the visual system, and then you have the cognition system, and then everything that is processed in between is a set of neurons that actually propagate the information from one part of the system to other part of the system. And then I'll show you how it is actually connected in the computer science. But then just to give a brief introduction here is that you have wide variety of applications, all ranging from everyday use case all the way to the finance, something more advanced. And since we are talking about the AI, and I was also looking at some of the areas in the AI, what we are talking about, and then there seems to be three different categories of AI. The very first one, what we call as narrow AI, which is more reactive machines. So we ask something and then the answer is given to us. So these are typically called reactive machines. And then there's also the limited memory machines, which operate on the specific concepts of AI. And then there is this general AI, which is more on theory of mind, which means that human-like cognitive abilities, such as if a human can do certain thing, so the machine should also be able to do that thing, right? So the idea is that we are somehow developing the theory of mind in that one. And then is the very third one, which is very hypothetical, which is super intelligent AI. What they're talking about, at least the field is talking about, is having this human intelligence and even to the extent of surpassing it, right? So again, at this point of time, it's very debatable, it's very hypothetical, so people are talking about that, but just it's not implemented yet. I think we are in the phase of general AI right now. So we are somewhere in this area. So this area, there have been some works. Most possibly, we are not aware of it because the companies might not have published. But we are on the verge of reaching that one. Maybe in a couple of. So I think, in my personal opinion, super intelligent AI would be the prime of everything, right? So when they're able to think and make decisions themselves, and then we are already there, right? Again, this is something very debatable, but just to be very clear on my views here, I had to go look into the website on NASA, and then they have the classifications. According to their classifications, super intelligent AI. Okay. Good. Again, why am I talking about all these things? I asked you about how many of you have done ML, DL, and so on. In that case, I wanted to put everything in context. And here you see that whatever we are doing is like the core aspects is machine learning, right? So within the machine learning, there is a subdomain which is deep learning. But now when you put a lot of things together, then it becomes an AI system. So this would mean that AI is almost like a simulation of human intelligence. And then there are subfields such as machine learning, natural language processing, robotics, and so on. You can place them inside that bigger circle. And the goal in any of the AI system is to build a system that can actually perform equally to an human with the same level of intelligence, right? Now, again, this figure itself, I've oversimplified this, but if you go a bit deeper and then you start looking at different topics, then you can see that there is even finer classification of this taxonomy. Okay, so why do we talk about the machine learning? In any case of the machine learning, what we are looking at is that we are trying to learn from the data, right? So any kid who is trying to learn how is an apple different from an orange looks at certain characteristics, and by looking at number of different examples of apples, so he starts looking at some new apple and telling that, okay, this is an apple, right? So we are purely learning from the data itself. And now, in the case of in the realm of machine learning, what we are talking about is three different aspects. One is supervised machine learning, unsupervised machine learning, and then reinforcement learning. And irrespective of what we are talking about, everything comes down to this small equation here. We have a function which is a function of x and theta, right? Now, x is the data that we are looking at, and then theta is the parameters that we are learning. For instance, if you are learning on classifying between apples and oranges, or let's say apples and bananas, so what we are looking at is we are looking at shape and the color and the let's say even the texture and so on, right? So these are all the features that go inside, and then we are learning a function which is called as f of x and theta, and that theta is what derives when is something an apple versus when is something an orange. Okay, so we'll come back to that later on. But remember, everything that is in machine learning is that small formula, right? Okay, even before we jump into the AI part itself, I want to have some understanding of statistics. I want you to have some understanding of probability and so on. So everything that we do in machine learning is about creating a hypothesis and then testing it out and making an inference out of it, and then validating that this hypothesis was right or wrong, right? And this is very central to the probabilistic reasoning. A lot of these models that we are learning today are Bayesian models, and a lot of these are related to hypothesis testing. I'll not get more into this, but I'll give you some examples of how we do this. Whenever you're talking about the statistics, we are talking about two different aspects. One is descriptive statistics, such as we can describe the data, right? So if we look at a data, then we see that, okay, this is a particular mean, there is some amount of median, and there is a particular variance in the data. And then we can say this data has a mean of x, and this variance is sigma, and so on. And then you have the other side of the statistics, which is more on inferential statistics, which is typically based on your population. So when I say population, I would say that, okay, people in Jaipur are very nice. So that means that it's based on some inference, right? So I'm looking at the statistics from previous years, and then I come to a conclusion. Okay, so we make use of both of these things in a number of different concepts within AI, but just to have a higher level taxonomy, these are two major kinds of statistics. And then for everybody that has taken a course in mathematics, you know how the mean works. It's typically the average of all the data that we have. Let's say the average height of this class, we would look at the total number of people, and each of the height is recorded, and then we average it out, right? And then we can say, okay, the class of Gyan course had so many people with average height of X meters, right? That forms a very central aspect of the machine learning. And then comes the second aspect, which is the variance, which would mean that how much is somebody differing from the regular population, either to the positive extreme or to the negative extreme. I'll come back to this when I discuss about the distributions in a short while. But this also is very important, right? If the data is lying very far away from the mean, it has high variance, then we can already say something about that data point, right? And then comes the other aspect, which is standard deviation. Okay, although the distribution is Gaussian distribution, although it is, let's say it's not Gaussian distribution, then how much is the data varying from one end of the spectrum to the other end of the spectrum, right? So these three concepts, no matter what you want to do, you will never get rid of this one, right? So you always use them time and again. And now, why are we talking about the mean variance and the standard deviation? So any data that we observe, we typically end up in a normal distribution, which is approximately something like this, what I'm showing on the screen. So in this case, you can already see that there is the graph that starts from somewhere around -3, and then it ends at +3, and the mean is centered around 0. Right? So this is a perfectly normal distribution, which says that if the data lies in plus or minus some deviation, let's say one standard deviation is around -1 and +1, two standard deviation is around -2 and +2, and three standard deviation is around -3 and +3. So then we can already start thinking about how close is the data point that we are looking at, right? So then are we talking about the data that is very abundantly available, or are we talking about some rare incidents? So the rare incidents might end up in this tails, which we call as long tail distribution problems, right? So we can come back to that later on. But very often we model everything that we want to do in machine learning based on the assumption that it's a Gaussian distribution. All right, and then I just gave the brief motivation on mean the variance. It typically distributes, or it kind of represents the spread of the data around the mean, and the standard deviation gives you the indication of how much is the variance in the data. And then comes the very central part of the machine learning, which is or AI system. Let's say it's one of the theorem called as Bayes theorem. So why should we be worried about, or why should we be aware of this Bayes theorem? Is mainly because you have this probabilistic inference, and everything that we are making an inference is about having some prior probability and then coming to a conclusion, right? Now that I've seen that there are 20 cars driving in the streets of Jaipur, and then I've seen all of the cars are white in color. So what is the probability that the next car that is going to be driven on Jaipur streets is going to be a white car, right? So you have some observations, and then you have some estimate of the probability, and then you tend to make an inference out of it, right? So you model them on these aspects, which is nothing but the notation is quite simple. So you say A given B is nothing but the probability of B given A, multiplied with the probability of P of A divided by the probability of P of P, right? So each of them are individual independent probability distributions, and then we put them together, so then we can make an inference. And then there is also this other aspect, which is called the central limit theorem. I'm not sure how many of you have heard about this, but I'm very sure that you all use this at some point of time. So the central limit theorem says that the sampling distribution of a sample, the mean approaches a normal distribution as the sample size increases, which means the more data that we have, it's very likely that the distribution is going to end up as a Gaussian distribution, right? So now if we don't end up there, that means that we have limitations in terms of data, okay? Even if the original data is not normally distributed, we will end up at that point at a given point of time, right? So the whole assumption lies on that area. And then why should we think about the central limit theorem, and then what is the relationship between the CLT and the neural networks? Any neural network, as I was telling before, is nothing but a weighted sum of random inputs, right? So two eyes look at a particular object, and the two of them are giving you some signal, and when it goes to the brain is actually summing up those two signals, right? So it's not, at any point of time, it's not one signal operating, but each of the different signals that is processed inside the brain is a combination of them. Now, if you want to somehow put that into a mathematical formulation, you can put it as the equation that is given here. And in this case, we see that it's nothing but some weights for each particular input plus some bias, right? And then the bias term is not the typical bias that we talk in the regular societal context, but it's a factor that plays a role in normalizing these parameters, right? Okay, and now here is the relationship between the central limit theorem and the distribution. So I told you that anything that we are looking at in the normal world, in the real world, is usually a Gaussian distribution. So when we have this Gaussian distributed data, then every single point is supposed to lead us to this formula, which we will talk about it later. But they all follow the assumption of Gaussian distribution here, right? So the only problem would be that when we don't have enough amount of data, then we might have to play with these parameters here. But any system that you would want to, you can model based on this one. And then there is also this other aspect, right? So for those of you who have worked on neural networks or AI systems, you typically have this flag of initializing the weights. So when you are initializing the weights, you are doing a random initialization. And the random initialization would mean that I can give the weights to start with 0, or I could say that, okay, I have seen a number of different examples, and based on these examples, I can say that the weights will start at a particular point. And this point, whatever we are choosing to initialize, this typically follows a Gaussian distribution, and that's where the connection between the central limit theorem and the AI systems come into picture. Okay, now I don't know what time is the break plan, Mahipal, so you can just stop me whenever. I can continue, okay. So you just tell me whenever I want to stop, right? Okay, and then comes the second aspect, right? The probability and distribution. So any system that we are looking at in terms of AI systems, in terms of neural networks, is about the probability and distributions. So which means that what is the likelihood of something happening, right? So if I have seen 200 patients in a day as a doctor, so what is the likelihood that I will see a patient today who has some indications of, let's say, breast cancer, some indications of lung cancer, right? So it's all about the idea of putting the likelihood into the picture here. And whenever we are talking about this kind of likelihood, we also talk about what is the distribution of the system. So it means that typically in a normal phenomena, natural phenomena, we go for Gaussian distributions, which means we have a certain amount of probability that follows this particular rule. Now comes the idea of using this mean and standard deviation, right? So now you can see the whole picture together. You see that all the data that I'm going to get are represented in terms of x, and then there is this data that is represented with the mean with mu, and then the standard deviation sigma. So all of them get connected here, and then you see that any probability, any particular probability of an event happening would follow this particular rule, right? So it's a generalized rule, but it's obeyed in many of the systems. And then comes the second aspect, which is typically a binary systems, which is having a binary output 0 or 1. Either it happens or it does not happen, right? In that cases, we are talking about the Bernoulli distribution, where we say it happens or it does not happen. Typical examples are raining, right? It's either raining or it's not raining. So you cannot have something in between, right? So you can have some sun and rain, but still it's raining, right? So the distribution is about here the probability of raining itself and the distribution of the probability of not raining in a given circumstances. And now why does this become important? In any of these systems that we are developing today, it's very typically binary systems, right? We are not yet reached the system where we have quantum computations available with us, but all the systems that we are using today, any deep learning system, they are typically this binary system. So they predict something A or B, or they say the likelihood of A being with some percentage and likelihood of B being with certain percentage. Okay, so again, for those of you who want to go a bit deeper, you could always go to other distributions, and in some aspects, some other distributions are much more informative than these two distributions, right? So know your data beforehand. And then just I'll not spend a lot of time on this one, but just to give a simple relationship between the statistics and AI. any AI system, we are willing to make a decision, right? Or we intend to make a decision. We want to say whether this is an apple or this is an orange. And when we're trying to do that, we create a hypothesis. Given that we have seen so much amount of data, so I see this could be an apple, and now that is my hypothesis. And if that is the hypothesis, then we start that it's a null hypothesis. And then we also create an alternative hypothesis which says that, okay, well, it's actually not an apple, right? So the way we evaluate the system is by looking at the observations, and then we say that if the data, given the data, if it follows the null hypothesis, then I should get a p-value, and any p-value which is less than 0.05 is valid, and anything that is greater than that will tell that it is not statistically significant, right? So now we cannot completely reject the hypothesis, but we don't have sufficient evidence to support the hypothesis, right? There's a subtle difference there, okay? So this forms again the basis of any decision making system, right? So if you take the medical classification system, specifically if you want to say that, okay, when I look at a particular image and I say that this image is cancerous, or this person has cancer, then I would be wanting to say it with confidence, right? If I don't have enough observations to support this argument, then I would say that, well, I don't have statistically conclusive evidence to say that this is cancer. Now, this becomes central aspects in many of the machine learning systems where explainability becomes a core concept. Okay, and now just to go back to touch upon some of the basic aspects, I saw that many of you wrote linear regression. Now, how is linear regression connected to AI, any system that we are looking at? So in any given linear regression model, you have some input features, and then let's say that the features are spread around different area, and then you would want to fit some lines, right? So in this case, if I take this particular aspect, I say that here is the number of data points, and the data points are lying around in a scattered way, and then I create a relationship between them. And now the relationship is nothing but a simple line, right? So most of you had studied the mathematics or the calculus part. So you start with the equation to the line, which is y equals mx plus c, right? And then c is the slope, and then mx is the coefficient that derive how the lines are. And this exactly is what we are doing in machine learning. So what we tend to do is that we create this decision boundary between two different classes. So you have apple classes, you have orange classes, and then you want to create nice boundary between them. If you are in a luxury situation, apples and bananas, yes, certainly fine, because you can clearly differentiate them based on the shape. But if you're talking about apples and oranges, they are very close to each other in terms of shape, right? So the circularity, the shape of the apple itself can be sometimes like shape of orange, and that would mean that you are not going to end up with this perfectly clear line, which is like y equals mx plus c. And then what happens is that we try to fit a line. So when we are fitting the line, we use a method called as least square methods, where we are trying to minimize the distance between the error, between the observations and the error that we are seeing, right? So again, the idea goes back to having the fundamentals in the back of the mind. Now then, if we are able to do that, why should we even think about using the deep learning networks? The problem comes with the computational bottleneck. So which means any kind of system that we have, it requires some kind of closed form solution. So whenever we are talking about closed form solutions, we are talking about this matrix inversion, right? So those of you who have taken the matrix, the linear algebra, calculus courses, you know that inversing a matrix is not an easy task, right? Now we are talking about a matrix which is 3 cross 3, which is okay, we can derive it on paper and then invert it. But imagine now an image which is megapixels. So every time you are talking about a simple face image which you are taken from your smartphone, to invert that matrix becomes very, very expensive, right? So if you have to do some operation on that, if you want to say that whether this person is Maipal or if this person is Kiran, then if you take 20 minutes to make such a decision, then nobody wants to wait for 20 minutes, right? So then you are reducing the usability of that particular system. So in that way, it's very intensive in terms of computation. And then also the intermediate operations in this whole pipeline has to be saved. For the time being, don't worry about all the mathematical notation that I'm putting. I'll come back to it later on as we proceed. But just remember here that there is an aspect of this inversion, right? So there is data X, the matrix X, and then you take the transform of that, and then you multiply with the original matrix itself, and then you take the inverse by doing this operation, and then multiply, and then again there is a data, right? So it's not very convenient. It's not very super user friendly. And then there is the other aspect, linear regression. Although it's very elegant, one of the major problem is that online learning. So what do I mean by online learning? Today I have seen 20 examples. So based on that, I have learned a new system, and tomorrow comes a new example, right? So when the new example comes in, I want to update that. Maybe it's a rare event, but it still is an event. I want to update the system. So what do? I have to go back and relearn the whole system, and that is again expensive, right? So in which case, continual learning or online learning is not very feasible with linear regression. One example is also that you have this spam filters. So very often when you open your Gmail, you say that, okay, maybe this is a spam, right? So, and then you say that, okay, well, this was actually a spam, and then you click on that filter, and then next time you get that mail is automatically categorized. Now, how does this happen? It happens because there is like online learning happening, and it looks at the new data and it updates the model. So that is another problem with the linear regression. And then there is also this other bigger problem. Those of you who are working in theoretical computer science, theoretical mathematics, you know that there is numerical instability with linear regression. So inversion of any nearly singular matrix will lead to errors. That could be infinity errors, right? Okay, good. So I think we have now formed a basis telling that, okay, there is some amount of statistics, some amount of linear regression. Now, we also saw that there is a problem with linear regression. So what do we do from now on? So from now on, what we tend to do, we try to use something called as gradient descent, and it's an iterative optimization. So you start with creating the decision boundary, and then you go all the way from the bottom of the particular slope, and then from the top of the slope, and then try to find the local minima. I'll show it in a very short moment, but the critical aspect of gradient descent is that it works very well with the large scale data. And the moment we talk about large scale data, we are talking about this huge deep learning models, huge neural network models, which can actually make use of such data, right? And again, as an advantage, I told you that this online learning was a problem in linear regression. As soon as we go to the new part in the gradient descent, it is able to do that. So you don't have to relearn the whole system, you just need to update the gradients. So as long as you update the gradients, then you're able to take into account the new sample that has come in. And then it's also memory efficient, scalable in many terms. But the key goal here, or the key advantage here, is that you're going from exact solutions in linear regressions to something that is approximations, right? So why do we call it as an approximation? So I don't know if I should get into the details of this, but the idea again is a simple least square analysis, right? So if you look at the data, you have some data here, which is from the model itself, and then you have data that is ground truth, and then you try to take the error between those two. And now it's a Euclidean error here. You are looking at the function as the square difference and an average difference. And then the moment you do that, you can keep on updating the gradient. So the theta j is nothing but a theta j minus the derivative of this cost function that we have here, right? So as long as you have this one, so you're trying to change the learning rate. So if I encounter a new example, then I can simply go back and then change this learning rate and say that, okay, listen, here you are trying to, you seem to have some difficulty in learning these samples. Just go back and relearn it, right? Okay, just to give a brief illustration of what exactly happens. So in any kind of gradient descent optimization, this is what is happening, right? So you start with a particular point, and then you try to find the local minima. So in the first iteration, maybe you are there. Second iteration, you are coming a bit closer because it's again derivative, right? So you can follow the slope, and then you come to the next point, then you come to the next point, and so on, and so on. And at this particular point, you are come to the lowest possible minima, what we call as global minima, right? Now again, that's a different field by itself, but as soon as you reach this particular point, you can safely say that your system has learned something. And then that's when we say, okay, now that the minima is not increasing, so now I've converged to a particular solution. All right. So all the system that we are dealing with in the machine learning now, the AI system is mostly handling about or dealing about this gradient descent optimization. I relate to this in a short while how this actually is used in the systems. But now let's take a simple look at the machine learning, or maybe it's a good time to take some questions if there are any questions from the audience. No questions? Okay.
Just go to the previous slide.
Previous here, yeah.
That how that is minimize the loss function. Can you please
So how we connect this one to the loss function is that we always want to find this local minima, right? So once we have reached local minima, that would mean that we. It's a very nice question actually. So let's see here. So we have the predictions from this part. We have the ground truth from this part, and then the error between those two should be zero. Right? We come to that point by minimizing this part.
you have to apply the minimize cost function?
Minimize the cost function so that you get loss which is very low. So for those of you who did not follow the discussion, the idea was that how is that this related to telling that the network has learned something meaningful, right? So that means that we are looking at the loss of the information here. Okay, good. So then let's try to talk a bit about the machine learning itself, and then we can take a break and then come back and continue with the second part of the lecture. Let's start with the areas of machine learning. As I told, there are three different areas in machine learning. The first part is supervised machine learning, where I give the data and I also give the labels. I say, okay, these are the number of images of cats. These are the number of images of dogs. Now try to learn the difference between the cats and the dogs, right? So I'm giving the labels explicitly. And the common examples are classification, like cat versus dog. And the second example is about regression. So where I'm talking about, okay, if I know that a particular dog is growing to certain height, what would be the most likely height in the next month, right? So then I'm trying to regress the data. Another example is that for those of you who are looking at stock market, you probably would be expecting also that, okay, if the cost is increasing, if the stock is increasing to a particular value, what would be the most likely value in the next day? Either it goes up or it goes down, right? So that is what we call as regression. But again, the key aspect in the case of supervised learning is that we are going back with data, available data. All right, and then we have the unsupervised learning, right? Most often we have this luxury of data, but we probably will not have the luxury of labeling. For instance, in medical imaging, right? When there was COVID, the pandemic that happened, suddenly we had number of chest images. Everybody had chest images, but we didn't have data that represented how the COVID would look like in a chest image, right? So now what we are looking at, we are trying to cluster all the images that look very similar into one group, and something that is not similar, we put it into other group. So there comes the idea of unsupervised learning, where we want to look at the pattern itself without having any knowledge about the label, right? Nobody knew what pandemic, what COVID would look like before, right? So we had very limited labels. And the very common example here is also in case of medical practitioners, if they have to sit and look and label the data, they would never do that, right? Because saving a life is far more important for them than sitting and labeling the data, right? So this is very common application in unsupervised learning. And then is the anomaly detection. I'm not sure how many of you experienced when you went to a different state, suddenly your credit card stops working, right? And this is anomaly detection, because you are typically living in Jaipur, you are typically living in Delhi, and then you are using your credit card. So the bank knows that you are using the card in a particular area, and suddenly it looks like, oh, there is this person using the card in, let's say, in Bombay or in Bangalore, and then there is this anomaly, right? It does not belong to the regular pattern of a particular user. So there, unsupervised learning comes into picture, and then comes the reinforcement learning. The most common example there we can think of is autonomous driving. So you are driving through the streets of Jaipur. So the car has learned the system in Jaipur, and suddenly you decide for a weekend you want to get away from Jaipur and then go to maybe Udaipur or to some other place, and then the road systems may be different, right? So then the system keeps learning the new system, the new roads continuously. And then there is the idea of this game playing, which means you have this reward and punishment. Every time the system makes a nice decision, good decision, then you reward it. And then when it makes a wrong decision, you say that, okay, you know what, you made a wrong decision, you should be more careful next time. Okay, and then if you look at the connection between the ML and AI itself, machine learning is a very essential part of the bigger system in AI. And AI has a number of different learning mechanisms. One is this very old generation rule-based system, so which would say there are a set of rules, and then according to those rules, you would say this is the decision, right? One example is, let's say you have a particular person walking in the campus here, and then you would look at the person and then say, okay, this person is wearing a badge which is having a tag that is blue color, which is most likely that he or she is a student, right? And then the set of rules always are defined beforehand, right? And then this is typically the one of the system that has been used very popularly. And then there are expert systems, which are a combination of different set of rules, and then there are additional things coming into picture. And then you have the third aspect, which is learning from the data itself. And learning from data is more interesting for us, right? For the aspect of many different models, such as image recognition. So in this case, the models are trained to learn some patterns. One classical example is detecting the objects. So if there is an image, and if you want to look at the particular image and say, okay, there are two people in this image, then we want to look at the face, right? So we want to identify and spot the face in that image, and then we can make a decision telling that the pattern looks like its face. That means that there are two people in this image, right? So this is the fundamental task in many of the ML models. Okay, and then just to come to the supervised part of the machine learning. So this is how any pipeline would look like. So you have data, and then you try to train that model, whatever the model you would want to, right? You would want to train a SVM, you would want to train a linear classification, LDA, QDA, whatever you would want to, whatever is your favorite, and then you try to make a prediction here. And the idea here is that whenever I'm talking about data, in the case of supervised learning, I also talk about labels. So labels is nothing but the ground truth of the data itself. And then comes the aspect, right? So there was a question about what are neural networks. Now these neural networks are typically a combination of biological neurons, and they compose of three key aspects. One is the input, the second one is the hidden layers, and the third one is the output. Let's try to relate it to the human brain, right? So input is nothing but the things that we see, the things that we touch, things that we feel. So that goes as the input. As soon as it goes as the input, then there is number of things that is happening within the human brain, and those are all hidden. So there are a number of layers that are connected one to the second one, and then the brain makes a decision which is telling that, well, this is an apple, this is an orange, and so on. So three components becomes very essential, and each of them, not all the neurons get excited, right? So when I'm looking at apples, maybe some neurons get excited, while when I'm looking at some other object like a car or like a vehicle, then some other neurons get excited. So although there are n number of neurons, it's only some part of the neurons that get excited, and this can be modeled as a function of x and theta, right? You remember I showed a very simple equation, f of x given x and theta, and this exactly is that function if you want to expand it a bit further. Now, how does this happen exactly? So I have two input, let's say x1 and x2, and then I have number of hidden layers here. For the sake of simplicity, let's assume it's a one layered, one hidden layer, and then you have an output here, right? Okay. All right. So let's start with this very simple model, right? One where we start with the left side. The inputs are coming inside, and then we have three different nodes which are hidden: H1, H2, and H3, and then all of them are combined together here to get an output. No, it's not charging. Okay, so while
कुछ हटाओ मत, वो हटाना नहीं है अपने से सुनो।
ये चार्जिंग का मैम चार्जिंग कुछ हटाए नहीं
चार्ज हो रहा है
ऑनलाइन लिंक
चल जा रहा है. Okay, I think no, that is fine. But the charge.
चार्ज नहीं हो रहा है मैम से
चार्ज दूसरे पॉइंट पे हमेशा
नीचे वाले में
इसमें
चार्ज हो रहा है
All right. So while the charge is getting fixed, so what I was telling is that you had two inputs and then you had three one simple hidden layer, and it's a combination, right? So you add x1 with h1, and then you get an output, and then that comes as a y. So it's a very simple modeling, right? You have two models, three neurons here, and then there is an output here. So if this is x1, so it goes input to this one, and this one, and then h1, h2, h3. Now I could simply say that it's a combination of these ones, right? So it's nothing but, if you make it very, very simple, extremely simple, so I could say that it's some weight 1 times x1 and weight 2 times x1, weight 3 times x1, and then you make a combination of all three aspects. So which is exactly what's happening, right? So you take one input and then you combine it with the neurons here, and then you get an output from this particular aspect, and then you start measuring the difference between the prediction and the input itself. So whatever I'm getting here, this y-hat, this one becomes more critical in the case of the deep learning systems. So what we want to do is that we want to get that y-hat as close to the ground truth itself, right? So that is the loss function that we were talking about before. So the difference between the prediction and the original input should be very, very minimal. Okay. Now this looks very simple, right? So you have the input that goes from here, and here comes the idea of forward propagation. What do we talk about forward propagation is that we have this input, and then it goes from first layer to the second layer, which is the input layer, to the hidden layer, and then from the hidden layer you are going to the y output. So now you are looking at the propagation which is going from one way to the other way, right? From the input all the way to the output. And if you take it in a perceptron model, the very oldest model, which is also simplest neural network, neural unit, a binary classification task can be seen as, okay, whatever I'm getting from that one, the weights of different parameters and the input itself with some bias factor, B. And then I can say that I can put a simple binary thresholding which says sign, either positive or negative. If it's positive, it goes to class 1. If it's negative, it goes to class 2. Right? So that is again connecting back to the previous slide that I was showing you. Now, the other point is that sometimes, very often, it's not very linear in terms of relationship. So which means not everything can be a simple line. So that would mean the decision boundary that we are talking about may be something else other than simple line. So what we often use is that we use this activation function such as sigmoid, which is again a combination of 1 divided by 1 plus c to the power of minus x, or tan normalization, tan activation function, tan h, which is again function of exponentials, or we can also use this ReLU, which is called as how do you say? I'll come back to the ReLU part when we talk about this later on in the later on lectures. But at least you see that the activation functions doesn't necessarily have to be linear. And then here is the loss function, right? So I told that whatever we are trying to do, we are trying to achieve this minimum. So why do we need to achieve this minimum? Because we want the difference between the ground truth, which is y, and the prediction yi to be as low as possible. In the case of mean square error, we are simply taking the square error of these two, and then we are trying to average it out over the entire number of samples. If a machine learning model is able to give an error rate which is smaller, then I can say that it gives an average error that is quite low, then I can prefer that particular model. So very often we choose the models based on the loss that we get. And then there is also the other function which is called cross entropy, where we look at the information, the loss in terms of information theory, and we say that okay, the difference between them in terms of the ground truth and the predicted output here should be very low, right? Again, the only difference between the mean squared error and here is that you still use the two part, which is the ground truth part and the prediction part, but you slightly formulate it in a different way, right? So in both of these cases, the goal of our systems should be to minimize the loss function. Okay, all right, and then you have the forward propagation, right? I told you that it goes from A to B, B to C, and then you have an output, and then it's not as easy as that.
Can we take break?
Yeah.
15 minutes.
Okay, we can. Let me see. Okay, we can take the break now and then come back and continue. All right. Yeah. Okay, before we take the break, are there any questions that I should prepare before we take the next lecture? No? Okay. So then we take a break.
So we have tea arranged for the questions. It is in the menu.